Okay, so you saw some reductions yesterday, and the idea is to see some more reductions today. If I may catch you, Sukanya, if I may. Okay, so first day I asked you. Exactly. Do you remember the reduction now? From 3 sides. Okay, good. So I want that reduction today, and for different set of reasons. Yeah, to tell me, right? I mean, just I'm sure everybody knows it, but it's just that I still wanted to come up with a reduction. Okay.
So for every letter, for every variable.
So suppose I have a phi over, say, variable x1, x2, xn, and clauses c1, c2, cm. What are you doing?
So now for every variable,
For every
xi, create two vertices, xi and xi bar. Yeah, join them with an edge.
Very good. Hold on. Do you know what is this? Matching.
Yeah.
But it is doing something more.
It is ensuring that you pick exactly one of xi. Oh, sorry.
That's correct. At least one, exactly one. But there is something more fundamental happening here. If I have to make phi, don't guess Vaishali. Patience. Okay? We want to construct G phi with some property, some L. And what we would like to prove? Psi is satisfiable if and only if G phi has a vertex cover of size at most L. Agree? Okay, on purpose. Okay? Excellent. Now, if it is satisfiable, some assignments will be there, right? How many possible world of assignments of satisfiability are there? 2 power n possible assignments. I don't know which assignment, but there are 2 power n possible assignments. And when you make this gadget, now think of this gadget. This is the simplest gadget you could think of. It actually means a lot of things. It means your assignment implies selecting something, either selecting this, selecting this, selecting this. How many possibilities of selecting? 2 power n. So there seems to like a bijective correspondence between what I can select as a satisfying assignment and what I can select here, right? So in some sense, this is why it is called selection gadget. Right? Now I have selected objects, okay, right? So this is like, this is not anything else. What I try to do, like I'm trying to, so when I go to the reverse direction, I have to select objects such that it will correspond to satisfying assignment for my phi. Now, I don't know what this assignment will be, but here is the way to select things. Now, why matching? Because matching and vertex cover are correlated to each other, okay, in certain sense, okay. And then you have a budget which will force something. So like budget, gadget, relations, but fine. If I have a satisfying assignment and I can stop here, if you notice, then I say it has a vertex cover of size n, okay, if and only if. So forward direction will hold. If G has a satisfying assignment, then it has a vertex cover of size n. Just pick the corresponding guys. But if it has a vertex cover of size n, it may not correspond to a satisfying assignment of this, right? Because I can just pick all these guys, right? So I need to add more to this gadget than what it is, right? So that whatever I select, it forces us that these clauses are satisfiable. Okay? All right? Great. So what should I do now?
So now make gadgets for clauses. So every clause has at most
Say exactly 3 variables.
exactly 3. So make triangles, like join all those 3. So this is like
xi, xj bar, and say xk. So what will I do now?
now connect. So there are on the top you have some
xi.
margin. Yeah, xi now.
Let's call it x1, let's call it x2, let's call it x3. Doesn't matter. Just for
Join an edge between the corresponding ones.
so x1 you want to join to x1, x2 you want to make it join to x2, and x3 bar you join to. Okay? And definitely you need, if you need a vertex cover, you need 2 guys. So you will put a budget of 2m plus n, right? Which will force you that, like now this is an utility of budget. Okay? Here, what does budget tells you to do? Budget forces you that from each of these triangles, you have to pick 2 guys. So you are forced to select 2m guys here. And from here, you have to select n guys here. Okay. So is that all? Now can we go? So forward direction is perfectly fine, because what will I do? I will pick up an assignment from here. That will mean there is an empty spot here, right? Now look at any triangle. It satisfies. So it satisfies because someone has been set to 1. Okay, if someone has been set to 1, then that guy doesn't need to be picked, because that has been covered, so I can pick the other 2 remaining guys, right? Now backward direction will force us that, okay, fine, you picked up 1 guys here. Okay, now I correspondingly I say, oh, this is satisfying assignment. Why it is a satisfying assignment? Because, oh, suppose not, then look at this clauses, you only have picked up 2 guys, who takes care of him? That guy takes care of him. I mean, just simple, there's nothing more. Excellent. Imagine yourself that I was not reducing from 3 sat, I was reducing from sat. What will I do? Make what? Can we make a cycle? Why not? What's wrong in it? Maybe let's assume that this SAT formula has all clauses are of odd length. Are of odd length. Suppose. Just because it's like 3. Right? What happens? Right? And and then my is n plus clause is odd length, summation I going from 1 to m, this. Is this correct? Yeah, I don't think there's anything wrong in this proof. Look, if I use this as my object, okay, then what's problem? If phi is satisfiable, something is satisfiable, that will force that one of the endpoints edge is covered, so you delete that. Now you have odd number of vertices, and I can take half the vertices to select that as a vertex cover. Am I right?
No, here if you have lesser number of variables.
Look, my budget is exactly, I mean, look, every guy, every odd cycle needs some vertices to cover it. And you at least need that plus 2. If you have 5, you at least need 3 guys. Right? And I have only have given budget exactly as much as it is requires. Right? So every guy, so there will be a guy who will not be covered. Look at any, say, 5 length cycle. You pick up any 3 vertex. Whatever you pick 3 vertex, I mean, if you pick up 3 vertex, suppose this and this I picked. Now, clearly the edge which is incident to this guy is not covered. So but who covers up these guys? Oh, so there's a problem there, no? So what should we do? What happens if I make it a click and make it a click, and now I make it this? Well, this worked then. Now I think it works. Because I'm allowed to leave one vertex, and that one vertex can be taken care by the on the top. Okay, good. No, that's all. Okay. What is cluster vertex deletion? Huh? Is click. Okay, excellent. Great. So suppose look at this G phi graph. Okay, look at this G phi graph, and let's call this vertices V variable. Okay, what is its size? Huh? V variables. You added no some 2n variable. Excellent. So what is the cluster vertex deletion set of this graph? So cluster vertex deletion of this graph is definitely, or CVD is definitely less than equal to 2n. Agreed? Excellent. Now number of variables n and CV. So let's write down here variables, and here CVD. Here n went to 2n. And suppose I told you that for SAT 2 minus epsilon to the power n algorithm is not possible. Is not possible. Then can I say vertex cover parametrized by cluster vertex deletion set does not have and what is cluster vertex cover parametrized by cluster vertex deletion set? What is vertex cover parametrized by cluster vertex deletion set? Input is G set X subset of VG, which is cluster vertex deletion. Okay. Parameter is mod X, say K. Question: find minimum vertex cover. Minimum vertex cover. And what is an algorithm for this? I look at my X, here a click, I guess which vertex from here goes to cluster vertex deletion, I delete it, and for the remaining I take all its neighbors because I have to take it, and from the remaining click I find the minimum vertex cover, right? So clearly I can do this problem in 2 to the power k time. What does this imply?
Could you please repeat the problem?
So you want to find a vertex cover, but you're also given a cluster vertex deletion set X, and you are parameterizing by cluster vertex deletion set, right? So here is my algorithm for for finding minimum vertex cover. I guess which subset from this set X goes into my vertex cover. So I delete it. Now remaining guys are not going into my solution. So all its neighbors will go into solution. I pick it. Now what is left is disjoint union of clicks. I can find my cluster vertex deletion set in polynomial time. Sorry, minimum vertex cover on this disjoint union of clicks in poly time. What? Leave one, take all, leave one, take all, leave one, take all, leave one, take all. How much running time is? 2 to the power k. And what did I show to you just now? I am claiming to you, you cannot have root 2 minus epsilon to the power k algorithm for VC parameterized by CVD. Didn't I prove this? Imagine that if you had 1.40, not 414, 40 to the power k algorithm for CVD parameterized by, sorry, vertex cover parameterized by CVD. So what will I do? I look at my SAT, I gave this big huge thing and I say, hey, I know it has a cluster vertex deletion set of size 2n. Solve me minimum vertex cover. It will solve me minimum vertex cover. If it solves me minimum vertex cover, I know how to get a satisfying assignment. But how much time it took? 1.40 to the power 2n, which is strictly less than 2 power n, no? Like, which is actually less than some 2 minus epsilon to the power n. Epsilon is a fixed constant. Now you see why I asked you to. We must know these things in the first lecture. You will see more of its, more morphosis of this throughout the next 2-3 lectures, and then you will value this reduction. Okay? But that is not why I was trying to teach you. Okay? We'll get to these things much later. So notice I just gave you, I just wanted to show certain things about this. So it's a very interesting question at this point of time, no? Is 2 power k optimal? 2 power k, because root 2 to the power k is not possible, right? Or root 2 minus epsilon to the power k is not possible. Maybe 2 power k is optimal, that the trivial algorithm which we made, maybe that is an optimal algorithm. Can we come up with a reduction where the number of variables becomes just n? If somehow I would have been able to come up with a reduction where the number of variables would not have been 2n, but some n plus poly log n, then I will root out 2 power k algorithm. Then this trivial algorithm is an optimal algorithm, assuming SAT does not have such an algorithm. But that is not why I was trying to do this. So the reason why I brought this up, this reduction, look at here, when we are trying to do a gadget here, right, every variable, every clause, right, is contributing to the solution. Every ingredient is contributing to the solution, the size and this and that, right? But in parameterized reduction, like I cannot make gadgets for per object which is there in my input. I have to make gadgets which are like I have to make gadget for per solution vertex. That's a basic difference. I have to make a gadget which is in some sense proportional to the solution or proportional to the parameter which we have in hand. You understand? That is what we have to make. And that is where the difficulty comes, right? For example, here what we had to control, if you didn't know this and I said, show me a reduction from SAT, okay, where cluster vertex deletion set is a small. The problem becomes very, I want a reduction from SAT to vertex cover such that the instances that we create also has a small cluster vertex deletion. Now what we have, number of variables has to be related to the cluster vertex deletion solution which we have in head. Now I don't know what to do with the variables, clauses, because look at SAT instance, it could be very huge and amount of information probably we are trying to store for the parameter is maybe not even 1 bit per object. So we need more deeper way of gadgeteering, more difficult gadgeteering than you see. And this is why lots of problems which are easy to show NP hard seem like you need a completely different form of reduction to show them W1 hardness. Okay. Okay, this was just a, so it was a philosophical, right? But I gave you actually an interesting reduction actually. Okay. I actually have proved more things, but we'll get to that reduction. Okay. take a picture of this reduction, this click reduction. Okay, this has started a journey in parameterized complexity, and I will tell you the story when we reach there. Okay, so do you understand the? So when we reduce from click, right, give a reduction from click to our favorite problem, we are actually making gadget for k vertices of the click, k choose 2 edges of the click. Okay, so this is what I want to make explicit in this lecture today, right, that this is what we are doing actually. So here's an open problem for people who know. Is this reduction tight? Check the literature. Is this tight? Ashwin, do you know? Do you know the status of vertex over parameterized cluster vertex relation? Do we know better algorithm than 2 power k? Or can we show it's a lower boundary side? So it's unlike if it is not known, then it's an open question. If it is known, then also let's know. So please, some one of you just check the literature. It's nothing more than that. Okay, and if not, then by end of Saturday we should try to make such a reduction. Class project. Okay. By the way, this is what is called a strong exponential time hypothesis. Okay. But no, but we'll get there in a cleaner fashion, not like this. This is a hack. Okay. Okay. So let's do a balanced vertex separator. Unfortunately, for some time to come, you will only do this. So it's better that you get used to this problem. And on purpose, this problem has been chosen to tell you that it's just hard. Okay. So the problem which we are going to consider is balanced vertex separator. Okay. So what Akanksha did yesterday is give you a bunch of reduction to make you familiarize with FPT reduction. What I am going to do today is give them some pattern. Okay. G and number k. Okay. Just to save space, I am writing parameter here, k. You can also do this in your papers to save space. Right there. So I am saving space. The question is, does there exist a set S, okay, of at most k vertices, okay, at most k vertices, such that every connected component of G minus S has at most okay. So what is my goal? I want to find a small set S so that every connected component is at most half the this. Okay, this is my goal. And I want to give a reduction from click. Okay? Okay. So here is my G. Look, somehow what I would like to do is to, first of all, I know there is a click, right? So what I do, I take this, okay, subdivide every edge. Okay, and I'm going to call that WUV. Okay, I'm going to call them say some WUV. Okay. This is my first thing. Okay. My idea will be is that okay fine. So how many vertices does this graph has? Huh? Huh? N plus n choose 2? M choose 2?
For M.
Okay. But I will do slightly differently. Okay. So what you do first, so we have subdivided every edge of G. Okay. So currently it has n vertices plus m vertices. Okay. N plus m vertices because n and this. Now what is the property of original vertices? They are independent set. Right? I have subdivided every edges, right? Look at your, suppose this is a triangle, right? And now you subdivide every edge. Then look at the red edges, there is no edge between them, right? Okay. Now add a click on original vertices. Okay, add a click on the original vertices. Okay, so now let's get to the intuition part. My idea is, okay fine, now I have made this as a very big click and I have encoded edges where of my original graph. By adding this WUV, it tells me exactly precisely which endpoints have edges because they are not more than m and they tell you, look, if I am connected to them, then in my original graph I am edge, right? So it's like I have subdivided every edge and made, so this click is like dense object, right? Now notice if I have to separate, whatever I do for separation, right, these guys will stick together. This click guys will stick together, original vertices, right? This click guys will stick together. And notice one thing, if look at your click guys here, right? I mean, I will make it, so look, I have to delete some vertices such that some beautiful things happen. Now first of all, if I delete at most k vertices, this component is not going to be of the size half, whatever you do. You just check it out yourself. If you delete at most k vertices from here, suppose you deleted some s vertex from here and let's see what happens. How does this object look like? So suppose I deleted some s. This is at most k, no? Now look at the original vertices which are left here. How many of them are left there? N minus k. They are forming a click, so therefore, agreed? Now look at all the edges WUV who has at least one endpoint here. That guy is sticking out here, no? Look, that guy cannot go anywhere. That guy is sticking out. If I delete S, W, so the only WUV this guy has ability to separate out are those WUV who has both endpoint here, right? Because anyone who has both sides here, anyway the people who are both here, they are hanging with these guys, and anyone who has at least one neighbor is still hanging with him. So if I delete k guys, how many guys can I separate? Just check. K plus k, choose 2 at best. And so that is my intuition. I want to find set of k vertices from here such that it maximizes the number of objects of these singletons that he can separate out. And if k vertices has to maximize, that can only happen when it is a click. So that's an intuition. But now the problem is, if I delete this, I mean n could be very large, this is too large that this one component cannot be of any use to me. So how do I make it half? I just add another connected component of equal size. I add another connected component of, see, new disjoint, okay, of some size. Now what happens? If it is big enough, then this is half, right? Because I have to make half of total, no? So here's a trick. You just add a dummy object. So I just add dummy object. I will tell you of what size I will add. Of size L. Okay? So I will add a click on L vertices. And it is disjoint. And what is the size of L? I'll tell you what it is. It should be, okay, exactly n plus m. I'll tell you. K plus K choose 2. Because why? I will tell you why. I expect this click to have size roughly n minus m minus k choose 2, this big click. So I have just added some things of there, like so that, okay. So I have added L. So now what is the size of Vg prime? So let's call this G prime. What is the size of Vg prime? Notice here we had n plus m vertices. Edges we are not counting, right? Plus L. Okay, so let's write it down. It is 2 times n m minus k minus k choose 2. Is this correct? This is exactly what it is. So what is half? Right? So Vg prime by 2 is like, this is exactly precisely this, right? I am even subtracting more. So if this is my construction, okay, so my given G comma K instance of a click, I have made a construction G prime comma K. Right? This is what it is. Okay. So now let's look at forward direction. Okay. Forward direction. Look at this click. Okay. This guy is anyway good. Right? This guy is anyway good. Right? Now look at after I deleted it, what is this guy's size? Its size is at most are exactly equal to n plus m minus k, because I deleted k vertices, and since it was a click I have at least deleted k choose 2 guys. So minus k choose 2, right, which is less than half, right. So definitely if I had a click of size k, then I can delete this guy, then both components which are big enough has size at most half of my original instance. Okay, right. Look, I have fixed everything, right. I have encoded the edges of this click by what is intuitively, oh guys, you are so hard. The only way you can is that the guys which you are going to throw out maximizes the number of objects which sees them, which is exactly encoded my click in this way, and I have just added dummy so that the size becomes half. The reverse direction. Okay. You tell me anything. Is there any point of my solution to delete any vertex from clear? He is anyway a small component. Just at vertex. So that's okay. Agree. Okay. Reverse solution intersection. Let's call this KL is empty. Okay. Let's do another intersection. My claim is, why will you pick WUV? Okay, my claim is intersection, say let's call it W equal to WUV UV is an edge. Okay? Intersection W is empty. I want to prove this. Let's look at what happens. Suppose here I have UV, here's an edge because they are original vertex, and here is WUV. Okay. If you are picking him and you are picking none of UV, what is the point? Whom you are separating? No. Yeah. Huh? But what I could do, if I am picking WUV and say none of UV are selected, then I just delete V, put WUV to U, because if UVs are not selected, U and V are in the same connected component, right? Now I deleted V and added WUV, so I deleted by 1, increased by 1, so if so what does it mean? At least one of them must go to the solution, right? If suppose U goes to the solution, okay, fine. And why are you picking WUV then? Again, right? Delete V, right? And move WUV to the, look, no, you have deleted U and you have deleted WUV, both, right? Now what I am saying to you, no, so which is inside solution? U, right? And you have also picked up WUV. Okay, now I am saying delete V also, because now if you delete V and do not delete WUV, now WUV becomes singleton, so that's perfectly fine for us. And if both UV has gone, what is the point of deleting WUV? WUV is anyway singleton, so this is fine. Okay, fine, excellent. So I know that S comes from here. Okay, S comes from here. I mean, look, once the construction is clear, proof is like, is obvious because we have made the construction that way. It's not something which, I mean, okay. So let's do this proof, okay. We have to do 3 such more proofs before I go into philosophy again. So, okay. So now let's see, okay. So we have deleted, so S is original set of vertices here, okay. So original set of vertices here, and there is a big component, C star, and this is upside. Say P vertices are deleted, P edges. So what is this guy's size? Let's see. This guy's size is M plus N minus mod S minus P should be less than equal to Vg prime by 2, which is equal to N plus M minus K choose 2. Agree? Right? M plus N minus K choose 2. Agreed? This is what it is, right? M goes, N goes. So what are be left? Mod S plus P should be greater than equal to K plus K choose 2. My God. This can only happen when S is a clique. Because a set and double two-plate is greater than equal to K plus K choose 2. Right? And mod S is less than equal to K. You have to also use this fact, otherwise you are dead. Mod S is less than equal to K, right? And its two-plate is greater than equal to K choose 2. It means S has size exactly equal to K, and this two-plate forms a clique. So we are done. Question? No questions? It was so clear. Wow, I'm amazed. You will find this deduction in the textbook. It's not that, like, it's really a FPT textbook deduction. But remember this problem. Balanced vertex separator is W1 heart. Put it on your head, like stick it. Okay. You will see why I said this. Stick it to your head. Okay. So I'm rubbing. Okay. Okay. I want to do slightly funky thing. Okay. So let's see if this is FPT. Okay. Okay. So you're given a graph G, X subset of Vg, X subset of Vg, and the question is, and a number, and question is, find chromatic number of G. This is how it is chi G, right? Chromatic number of G. Of G. Okay, this is what I would need to find, the chromatic number of G. And my parameter is X equal to K. Can coloring parameterized by, suppose coloring parameterized by number of colors be FPT? Question. Can coloring parameterized by number of colors FPT? Why is it there?
Okay, equal to 3 also we know this.
Exactly. So even this will imply polynomial time. In fact, we cannot even have n to the power f of k algorithm because f of 3 is still poly. Good. So this is why we parameterize by vertex cover. What we parameterize by? Vertex cover. Is it FPT parameterized by vertex cover? Here is a vertex cover of size k. And here is independent set. Maybe you can make it a decision version of the question. Okay. Let's put, if find chi G. Is chi G at most L? So I don't. So if L is greater than or equal to k plus 1, what can you do? I want to say, is there a proper coloring of this graph with say L colors, where L is say greater than or equal to k plus 1? Yes, no, maybe, could be. How?
So everything other than the vertex cover, like G minus the vertex cover, can be given the same color?
Excellent. So you give I one color, am I right? And for every vertex here, use private color. Use private color. Excellent. At least I'm very happy that now people are. So what should I assume now? How will I make algorithm now? I guess a coloring of this guy. Okay. So I find a vertex cover, say C to 1 to L. How many such functions are there? L power k or k power L? So is it L power k or k power L? It is L power k. So let's fix one such. नहीं, अब तो मतलब धोखा हो जाएगा जी. Okay, so let's fix one such coloring, which is nothing but a partitioning of my vertex. Agree? Now look at independent set vertices. Let's say X. Look at the classes in which he has neighbors. Suppose he has a neighbor here, here, here. Then if this is a correct coloring, can X be put here? Can X be colored say 1, 3, 5? Can X, so let's see what all colors is prohibited on X. I see where he has neighbor. Oh, he has a neighbor in color class 1. 1? No. He has a color class 3. No. 5. If there is something left from 1 to L here, assign him that color and he's very happy, and you can do this for everybody else. If you succeed to do this for everybody else, you have found an L coloring. So basically, what we have shown that k power k is possible. An algorithm with running time order k power k is possible. Okay? Hopefully before Saturday I will show you this is all that you can do in your life. Okay? Nothing more you can do in your life. But I was not teaching you like FPT algorithm, so I have to change something, no? So I will say list coloring parameterized by vertex cover. So you are not only given a graph G, you are given X subset of vertex Vg, which is a vertex cover. Okay? Okay? Set of colors C. Okay? And in list coloring, for every V in Vg, you are also given a list of V which is subset of C, which means that these are the set of things which are allowed colors for this vertex. Task is to find a vertex coloring, right? Task is to find a vertex coloring C where CV, right, is inside LV for every V. So we want a proper coloring of my graph where I am not allowed to give any color. Every vertex must be assigned a color from its list. That's the difference between list coloring and a normal coloring, right? So we have say some set of colors and every vertex is has been given a list, he should only be assigned from this. Now if we look at our previous algorithm, none of the cases seems to trivially go through. Right? None of the cases seems to trivially go through. Right? At least I don't see. Okay? Hopefully you are also not able to see. And that is for some reason that we are not able to see. Not that we are dumb. Right? We are very smart people, but it's just that unfortunately problem is more smarter than us. So now I will show you something funky, okay. So we are going to give a reduction from what is called, I could give reduction from anything, but let's give a reduction from multicolor independent set. Have you seen multicolor independent set yesterday? Okay. Multicolor independent set. Okay. Basically you are given k color classes and you have to pick vertex from each that forms an independent set, right? So this is a multicolor independent set. Okay. Now here this is what. So I need to pick k vertices, right? So for each vertex that I am going to select to form a multicolor independent set, I am going to make a gadget for every vertex. One gadget. Don't write, it's useless. Sorry, but okay. So U1, these are my gadgets, singletons. U3, UK. Okay. And what is this gadget is supposed to do? From this class, he needs to select a vertex, right? What is my gadget? I am going to make a gadget, one gadget per solution object. So what is this is my gadget for solution which will pick up a vertex from here. So this is a one gadget who will select a vertex from this color classes. Okay. So this is called methodology, it's called vertex selection gadget methodology. So what should I do? I will say great. UK, I am supposed, so now I will give, what is my color class? Is V of G. My color class is all vertex set of my graph. Okay. You can think of them as 1 to n for all that you care. And what is list of UI is equal to Vi. which means what? You have to, in your assigned coloring, you're going to assign colors to these vertices, right? Which basically like picking a vertex from here, right? Which is perfectly fine, right? So whatever color you give, I have a corresponding notion of vertices here, right? So I have picked from each color class a vertex each. Now I need to encode what? That they are independent set. It means whatever object I have picked here and whatever vertex I picked here, suppose I picked up a vertex here and vertex here, there is no edge between them. How do I enforce that? So how do I enforce that? I said fine, look at your, yes, you were saying something.
I'm saying
Give the same color to whom?
to the vertices between whom you don't want an edge.
Here, make it a clear. So
Actually,
they can't
here
be given as.
you want
Click to whom?
Here, amongst
you
all
want
the
the UK
vertices,
should form an independent set.
But the vertices which you have selected, why are they forming independent set there? Look, I only have drawn k vertices, which are singletons. I have drawn nothing. You have to see, I have drawn nothing. I have just drawn k vertices and given them some big list. Up until now, all I have drawn is an isolated set of vertices. Okay? Look at an edge between two guys here. Okay, look at an edge between some vertex set Vi and vertex set Vj. There is an edge here. Okay, so for each edge, suppose this is between say U1 and U2, and it doesn't matter. Okay, so I draw a vertex. What is this vertex set? Okay, here is a blue vertex. Vertex corresponding to an edge between V1 and V2. So it is between some vertex A and vertex B. I'm going to make, let's call this whatever you want to call it, WAB is my vertex name. And what is the poor guy's list? AB, and that's end of my construction. So notice if I delete U1 to UK, what is remaining is an independent set, right? So what is the vertex cover of this graph? So look, I'm parameterizing my vertex cover. So the parameter has to be, not the solution size, parameter has to be bounded by the parameter in which I'm trying to show the reduction. So vertex cover here is U1, U2, UK, which size is bounded by K. Agreed? And now we have to show whatever we have to show. Okay, what we have to show? We have to show G has a K multicolor independent set, if and only if, let's call this graph G tilde, if and only if G tilde has a valid list coloring. Okay, great. Now, if G has a K multicolor independent set, so you go and pick. Okay, so U1, U2, U3 dot dot UK, you just assign that independent set from here. Okay, now look at any guy here. What is the property? Look, this vertex and this vertex are independent set. So the selected vertex does not have an edge. It means this guy, the list AB, it cannot be this as well as this. So there is some vertex, some color in his list which is not used on his neighbors, so I can give that. So that's done. Okay. Reverse direction. I have a coloring. All I need to show is that look at the coloring given at U1 to UK. Okay. Coloring given to U1, U2 dot dot UK corresponds to corresponds to vertices say W1, W2 to Wk in V1, V2 dot Vk respectively. So this is clearly multicolored. Need to show what? They are independent. And that is also obvious, right? Right? Suppose they are not, okay? It means you assigned some Wi here and some Wj here for some Uj, okay? Ui. And they have an edge. So look at this vertex W, Wi, Wj. What was his colored? Wi, Wj. But you said that you have a proper list coloring. This is a contradiction. So this cannot happen. So this forms an independent set. Done. Okay. So what did we do? Here we made gadgets for solution, and that's all. So this is what is called vertex representation reduction. Here for every solution vertex we had a gadget which selects everything else, and we just added some coherence between them. Question? Okay. So what is the key idea? The key idea is to represent the k vertices of the solution with k gadgets and connect the gadgets in a way that ensures that the represented values are compatible. Represented values are compatible. So let me write it down. I mean, not that I'm telling something very fun, very great, but still. So what is the key idea here? First is to represent the k vertices of the solution with k gadgets. And second, what we do, connect the gadgets in a way that ensures that the selected values are compatible, that the represented values or selected value, whatever you want to call it, values are compatible. So this is the crux of the idea. So this is what we try to implement it here. Okay, so let's do, I told you we'll do 4 reduction, right? We are only down to 1, 2. Okay. And now you will see, up until now we have only made gadgets for vertices, right? Select vertices. Now we also need to make a gadget for edges, otherwise we will not be doing correctly. Okay. Okay. So this is called odd set. Again, all this I am doing from the book, FPT textbook. Okay. So you are given a set system. F over a universe U, and an integer k. Okay. Okay. It's just a set S of at most k elements, set S of at most k elements such that S intersection F is equal to odd for every F in F, okay. So I am not looking for any hitting set, basically this is a hitting set because it intersects every set in F, but its intersection should be odd, 1, 3, 5, 7, 9, 11, 13, 15, 17, but it cannot be 2, 4, 6, 8, 0, okay. Okay. Again we will try multicolor independent set, okay. So now that I have talked about this problem, so what about this is my V1, V2, Vk, right. I make my universe equal to Vg for now, and this is my family. So my first list of family is V1, V2, Pk. Like this is my family which I try to create. Okay. Right? Multicolor independent set. So clearly in the forward direction I am going to pick something from here, something from here, something from here, one from each. But I need to do something, right, to make sure, I need to ensure that I do not pick an edge, right. I do pick an independent set. So how can I ensure that? What I could do is that for, suppose I have an edge, I could add to my set if AB, right, because look, you have to S of at most k elements so that S intersection F is odd. So now you are forced, right, from every edge you can only pick both. Huh? What? Yes, that's perfectly fine, no? So if you introduce the set AB in your family, you are forcing that exactly one of X and Y appears in the solution. Sure, you cannot have both in the solution. So you have forced this. Okay, what else can you do? But what's wrong with this? If I just do this much, what will go wrong? Huh?
It's not an independent set.
So forward direction is fine, right? Is it fine?
It will not hit this AB.
Do you realize what's the problem with this gadget is? Look, okay, I mean if I look at just this much, then this AB guy is not look, there could be an edge which is not, look at the K vertex you will select, red guy. Clearly you will not, you will hit, clearly you will hit, what is that called? You will select exactly K guys. No, so reverse direction, if you have a solution, then this is perfectly valid. No, look at what problem happened. So suppose in the reverse direction, if I had a K vertices which is odd set, then I am going to claim to you they form a independent set. Wait, they have to. In the reverse direction there is absolute, suppose I only draw this much, okay, and I go back, okay, I have a K guys which I have picked and I have to show that they form an independent set, right? Why are they not forming an independent set? Because there is an edge between two guys, but that's an edge, right? So then for each edge I have added a set of size 2. Wait, so I have only picked up exactly one of these guys, I cannot pick both because this set intersection with my solution is odd, so it has to be 1. So reverse direction holds. The problem is forward direction because I have added lots of sets. So I am only going to pick, in general, I am going to pick this k independent set vertices as my solution, right. Look at an edge which is beyond outside AB, for example, right. This is also an edge and neither A participates in the independent set nor B participates in the independent set, right. Then who hits this set? This set intersection with my independent set vertices is empty. So if I just leave it here, my forward direction doesn't hold. Reverse direction holds because all I needed to ensure that I do not pick, I do from each edge I pick exactly one, and that is a criteria of independent set. There is nothing more than that. So once I have put those two guys, I mean I have ensured that they are independent set. Okay. So this doesn't work as such. Okay. So what I try to do, okay, I could also try to do, suppose I have x, here is y, and there is an edge. Okay. So what I try to do, I try to introduce a new family of set which consists of x and contains v, say this is vi, this is vj, vj minus y. Suppose I introduce this set. Now notice what happens. So what you have done, you have actually picked up a set which is like this and which is like this, everybody else. Now if you pick x from here, then you are forcing that you must pick y. Because once you have picked x here, can you pick anything from here? Why? Why can't I pick anything from here? No, but I could pick exactly. So if I pick x, right, if I pick x, then I cannot pick anything from here because that will imply that I pick even and I only have budget of picking exactly one from here. Okay, so if I pick x, I am forced to pick y, but xy was an edge. We are creating trouble for ourselves. But suppose I do not pick x, okay. If I do not pick x, then I claim to you, you cannot pick y because you have to pick someone from here in this set, right. So what did we get? So we are getting two gadgets, which means either xy are inside or xy are both outside the solution, right. So like you try different sets of gadgets, okay. So if I just try to add a vertex gadget, this is the kind of trouble I face, right. And how do I handle this? I will handle this by having something called edge gadgets, right. So just like I am not able to encode, I have difficulty in encoding, just like I had a vertex gadget for each guys and I try to encode that xy does not go into the solution and I have lots and lots of difficulty, right. So now what I will say, fine, I will select vertices, I will select edges also, and later I will show to you that the selected vertices and selected edges together form a clique, sorry, together form an independent set, okay. Okay. So for some practical purposes, this is better to do from multicolor clique. So I will do from multicolor clique. I was just trying to show you, I mean, actually you can complement everything and do it, but it is a bit more intuitive in my head to do it from multicolor clique. Okay. It is a method, nothing changes. You want to pick guys so that they forms a clique. Okay. Okay. So now we have to so where are your edge gadgets going to come? Think about it. right? So if you notice there is something common happening here, and you pick up any reduction in parameterized complexity, this is exactly how things will look like. Of course, morphed. Okay. So these guys, look at a multicolored click. So I'm going to pick up one object from here, 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 one object from here. Edges. Together they form a click, right? So these are the set of objects which I need to select one object from for my solution. Look at your solution. Solution picks vertices, 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 and from two color classes and edges from the two color classes. So let me also do this now. Okay. So for just to show you some explicit example, let's draw 4 things. Not that it is helpful, but V1, V2, imagine that we have only 4 colors, okay. E1, 2, edge going from vertex class 1 to vertex class 2, edge going from vertex class 1 to vertex class 3, edge going from vertex class 1 to vertex class 4, edge going from vertex class 2 to 3, edge going from vertex class 2 to 4, and finally we should have 3, 4. So let's write down what we have drawn up until now. Okay. So what is my universe now? My universe is V of G, vertex set of G, union 1 Eij. Okay, which just tells us the edges going across color class I and color class J. Okay. Color class I and color class J. Okay, so this is what I have drawn. So now, what is my K prime? I have to pick one object from each of these guys, right? So that just forces you what K prime should be. So K prime is equal to K plus K choose 2. Now my F prime, my family, which F, what does it consist of first? V1, V2, Vk, okay, and Eij, I less than, strictly less than J, K, 1. So this many Eij's, okay, and then I have to add more things. This is not enough. Okay. Notice, what do I like? If I want a multicolor click, if I pick a vertex here, what do I want? I want an edge incident to that vertex to be selected, right? Am I not? If I want a click, then if I pick a vertex here, I would like an edge from here which is incident to him to be selected. How do I ensure that? Do you get my point? And there's a very easy way to introduce this. Look, if I fix this guy, what I want a gadget which is this, which forces that I cannot pick anything else because I have picked up this, and I only contain neighbors of him. You get my point? So if I have a set which excludes him, this, but now I have picked him, so nothing can be selected here, and what is rest left are all his neighbors. Look, this is why I was drawing before. If you select him, nothing can be selected. So I am just trying to make that idea go through. Okay. So for every V in Vi, okay, for every V in Vi and x not equal to I, and x not equal to I, for every U in Vi and x not equal to I, we introduce the following set. What should we do? Vi minus V and union what? Every edge incident to V, every edge incident to every edge from EIX, okay, incident to V. Look, if I fix V, he could have edges incident to several places, no? Right? He has edges incident to this color class, that color class, this color class, that color class, right? So what is this? Vi minus V and every edge from EIX with endpoint with V, and another set will be what? Every edge from EIX and x was not equal to I. So look, my V is here, right? Now x could be before or x could be after me, right? So look at 2, I'll draw an example, okay, in a minute. So let me write down every edge. It is just semantics, but all I am doing is for every vertex here, right, I am making a set in each class, I am making a V and making a edge set in each class which consists of this set and his neighbors. That's all that I am doing. If you look at mentally, this is all. It's just that I have to write because I could be first index, x could be the next index, and that is all that I've written. Every edge from EXI incident to V. This is just to write semantics, right? But actually what is happening, so what is this set? This set consists of this, everything here, and his neighbors here, V's neighbors here, the edges which are incident, same thing, maybe his neighbors here, same thing, his neighbors here, same thing, his neighbors here, same thing, his neighbors here. No, but it is in V2, so if it is in V2, so this cannot have, sorry, my mistake, 2, 3, 2, 4, this is it. Look, edges incident to V2 can either be to 1, to 3 or 4, right? So 1, 2 is here, it cannot be between 1 and 3, no? So 1, 3 only represents edges between them, so that will be empty. So this. And unfortunately, that's end of my construction. Okay, let's see why this is correct. All right, it should be correct by just our construction. Okay, I have worked so hard for my construction, so it's better be correct, no? Okay, so suppose you have a multicolor click. Okay, so you picked up those edges and vertices in this set, k plus k choose 2. Clearly, these sets are hit. Okay. Okay. Now look at these sets. Okay. Now look at any other vertex. Right. Look at the vertex which you are not selected. Look at a vertex which is not selected. Say W. A vertex which is not selected. Look at that set W. That contains V, no? Because how do I make my set? Remove W and add everything. So every other vertex which is here has been taken care, their sets are taken care because V is present there. Same here, same here, same here, same. So the only people whose objects are not taken care are those vertices which I have selected and the corresponding set. But look at that guy's corresponding set here. His one edge incident to him have been selected. So you are done. So forward direction is easy. Reverse direction. Budget tells me I pick one from here, here. Picked. All I need to show that the vertices and edges which I have selected forms a clique. So I have selected some vertices V1, V2, say Vk and some edges. Okay? And suppose they are not forming a clique. Why they are not forming a clique? So there is some V2, V3 which I have selected has, okay? Look at V2 and suppose V3, they have not an edge, okay? Clearly, look at the set this and this. Look at this set and this set. You picked up some edge, no? You have no choice. You have to pick some edge which is incident to V2. Fine. Again, you have selected an edge which is incident to V2, sorry, V3. So, why the same edge has been selected? You get my point? No. Okay, look at this V23. No? Look at a V23. There is a set which contains edges incident to V2, this and this. And look at the set which consists of V3 and H. Both have selected some edge row in the set here. So that edge is also incident to V2. That edge is also incident to V3. Because otherwise how can you pick the same edge? So this edge is incident to V2 and V3. So that forms a clique. Okay. So this is all that it is. Okay. There is no more funkiness. Once we have, so what did we do? We did both vertex. We made gadgets for each vertices of my solution. I made gadget for each edges of my solution and I put them together. Okay. Okay. So let's add to our key ideas. Okay. So what did we represent the k vertices of the clique or the solution by k gadgets? Okay. Represent, I will say no more solution, I will say clique because most reduction is from here, clique with k gadgets. Second, represent the k choose two edges of the clique with a gadget each. And now what should do? So slightly different. Connect each edge gadget Eij, okay, to vertex gadgets Vi and Vj such that okay, such that if Eij represents the edge between edge between x in Vi and y in Vj, then it forces, okay, then it forces Vi to x and Vj to y. Like if I have selected an edge xy, it forces that from Vi I pick the vertex x, it forces the Vj to pick the vertex y. So if you are able to come up with gadgets which satisfy these three properties, your reduction will go through. Okay? Okay, so maybe before I end my first lecture, let's see one more reduction, if you don't mind. I think I should have. Okay, but here I will just give the construction. I will not give you philosophy. Or maybe I will leave it. So read theorem 13.3 from the book, okay, 13.33. From PC textbook. Okay, it's the same thing. Okay, what's strongly connected? Steiner subgraph. So we have done all the reduction more or less, which is there in the textbook except this one. Okay, read just to get a flavor of these kind of things. Okay, so I think it's a good time to take a break, and let's come back. Huh? Unfortunately not. So you have to go there. Okay. So how many minute break do we need? 20 minutes? 20 minutes? Okay. So let's try to be here by 5:20. If you want to eat, do anything, and we will change track. So we'll come back at 5:20 and carry on with, I don't know till when, maybe till I die.